Once is enough, the one-shot instructions. In the plains of RS Logix 500 land, there lives a Micrologix 1000 processor. Although a very skilled processor, it is the least skilled of its family of processors. This controller was endowed with firmware that only supports one of the one-shot instructions, the OSR or one-shot rising. Micrologix 1000's younger brothers were born with firmware that supports all three of the one-shot instructions. The ONS, which is the basic instruction and yet identical to the OSR in the Micrologix 1000 for functionality. In addition to the ONS, it also supports the OSR, one-shot rising, and OSF, one-shot falling. I mention this here to provide a heads up to those who have used the OSR on the plains of RS Logix 500 with the Micrologix 1000 processor. However, in the mountain ranges of RS Logix 5000, the sky is the limit. We will address the ONS instruction in this next section. In the manual, I said you can begin with your existing project, delete all the logic and all of the tags, and save the module defined tags, which you cannot delete unless you delete the modules themselves from your I/O configuration. So in other words, you're going to strip this program down that you're looking at on screen here until there's nothing left but the module defined tags. And we save it as beginner, save as beginner L31 ONS. And of course we do that before we delete everything. I had it already saved as the older name. So now we can go offline because it's quicker. Go up to rung 0, delete, 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 delete. Program's all gone. Program tags. Edit tags tab. Hold the mouse button down here and drag it down to the bottom. Not all the way to the bottom. Hit delete. All the tags are gone from the program tags. Go to controller tags, and of course you cannot delete these. Well, I've never tried it. Not going to let you delete them because they're module defined tags that go with this module here. So you cannot delete your module defined tags. However, I did suggest that you start with a new project and name it beginner L, your processor number, ONS, and add the I/O modules that you are working with. This will reinforce this procedure that you exercised earlier. Practice makes perfect. I don't do that because I've done this so many hundreds and hundreds of times that I don't need to reinforce this procedure. But if you're learning, the more often that you start from scratch and create a new project, the better. In this case, I changed the processor. Right now we have an L31 Compact Logix. I'm going to change it to a different processor. I'm going to change it to an L35E. I'm going to name this then L35E. And I'm going to save the project as beginner L35E ONS. Now what I have to do is pause, and I have to swap out the L31 processor on my lab station and switch over to an L35E. Well, here we are with an L35E. You see I'm back in the remote run mode. And I have an L35E Compact Logix controller. It has a serial port, and I've got it set up for 38.4 just in case I decide to use it. Now I did not add the I/O module, or rather I should say I deleted everything, including the I/O module. I no longer have any module defined tags. Now to be honest with you, I created a new project and this is where it's at. If I had just changed it from one processor to the other, deleted the I/O module down here, the module defined classes of objects would still be there. Once they're in there, they don't leave when you take out the module. As a matter of fact, to prove that, now I'm online, So I can't add a new module, but I can discover modules. So I'm going to click on that, and it comes up, and of course it says that controller does not support adding I/O online. Okay, but it shows you the two modules. Well, it shows you, yes, it shows you the 1769. It doesn't say IQ6 OW4, but you see 24 volt DC input, relay output, combo. Then it shows the combo analog card. So you can see the cards, but you can't add them. So I'm going to close. I'm going to go offline. Right click on compact bus. But see, it doesn't support discover modules. So the L35E isn't going to allow you to discover the modules. You could look at them, but remember you can do that in RS Links as well. So if we go down here to RS Links and expand, there's the IQ6 OW4, and there's the IF4XOF2. Did I say IQ6XOW4? Sometimes I leave out the X. The X is like the X in 2x4, 2x8, 1x3, 1x4. The X in there just is kind of a delimiter between the inputs and the outputs. As long as we're here, notice that we are coming from Ethernet into an Ethernet port, and it shows a daughter card. Looks like a little card that you might plug into a motherboard. The cable plugs into that card, and that card is on the back plane of the system. Also on this back plane is the processor. This is the processor right here. You see a plus sign. The reason there's a plus sign there is because this processor has two ports. You see there it has two little black squares. Now that doesn't really mean anything, because if anything that looks like an L31, like it has two RS-232 ports, but it doesn't. It has an Ethernet port right here that's plugged into the back plane. Also plugged into the back plane is the processor. Now you think of the port as going into the processor. Technically it doesn't. It goes into an Ethernet card that goes to the back plane, and then the back plane also has the processor. Now here we see the Ethernet port again, and notice that this is identical to up here. The difference is this is the card. This is not. This is showing a placeholder on the back plane for the L35E. We discussed this at length when we were looking at RS Links. Also on the back plane is a local 1769 bus adapter. And this is the bus. This is the adapter, this is the bus. And on the bus, we have the bus adapter right here. Again, it's repeated. That's the bus adapter, this is not. It's a placeholder graphically to show you what is in slot 0. Then in slot 1 we have the IQ6XOW4, and in slot 2 we have the IF2XOF2. So we have the combination digital input-output, combination analog input-output. So as long as we're looking at this, I thought I would tidy this up. Now, if I expand this, remember this has got two ports. I came in through the daughter card onto the back plane, and then on the back plane I have the processor, a placeholder for this card up here, and then I have the local bus adapter. Notice that these two have plus signs in front of them, this one doesn't. If I right click on that, I get nothing, because there's nothing there. It's just a graphical placeholder. If I right click here, I get this. I can do module configuration, device properties, etc., which I don't want to do. But when I right click here, I get nothing, because there's nothing there. There's nothing. Now, if I expand the local bus adapter, I see that the local bus adapter it's plugged into the back plane, and it's also plugged into the local bus. And plugged into the local bus is the adapter itself, which is right here. and these two cards. If I expand this, the only reason that plus sign is there is because there are two ports. So I came in through Ethernet across the backplane, I go into the processor, and then I can go out the front of the processor on channel 0. And it shows that the Compact Logic's processor is on channel 0, but that's looking backwards into the processor, backplane, etc. Okay, so whenever if we did this the other way around, which we could, I don't have RS-232 plugged into that L35E, but if I did, and I think I did demonstrate that in an earlier video, the more you look at these pathways, the path of communications, the more you understand what you're looking at. I'm offline. I'm going to add a new module, and it's going to be the IQ6. That's enough to eliminate all the rest. We'll just do blah blah in slot 1. Now you see the module define tags are in there. The classes of objects, and this is the instance that you'll see in your controller tags. See, that's the class of objects, and this is the instance. So now I'm going to delete this card. And notice that the tags disappeared, but guess what? The classes of objects did not disappear. I said that when I started into the L35E, but I wanted to prove it to you. That once these are in there, they are available for you to use. Which I think there is a lab somewhere in one of the manuals that we're developing that I actually have you use this class of objects to create your own virtual I/O card. Because once these are in there, they're in there. See, you could delete them if you wanted to, but why bother? Okay, let's go back and add our card. It's an IQ6. DC inputs, relay outputs. I put 01 after it. That way we know it's in slot 1. And I'm going to change this to disable keying. That way I don't have to fool with it. It won't, when I try to download it and run it, it won't look at the actual version level and major minor firmware level to decide if it wants to communicate with that module. Okay, so now we're back in business. You're on page 176, 177 in your project manual. And in there, you know, I do point out that, again, that the main task is a continuous task indicated by the clockwise rotating arrow on the folder. That it means it just is continually trying to execute. The main program is a program indicated by the symbol on its folder. See the symbol right there? Looks like a little flow diagram. That indicates that it's a program as opposed to a phase. The main routine is the main routine as indicated by the symbol on the folder as opposed to a subroutine. This little piece of paper with a 1 on it with it dog-eared over, that will be the symbol that shows you graphically what the main routine is, because I can create another routine. I can right click, do a new routine and name it anything I want. We've discussed this before, we'll discuss it again. One of the places that we're headed is instruction help. And over the years I've gone to instruction help on more than one occasion, especially if I have not used a particular instruction in a long time. What you see here is the Logic's engine can be programmed with ladder diagram logic. We call it ladder logic diagram, LLD. It can be programmed with function block, it can be programmed with sequential function charts, and with structured text. Keep in mind that all 4 of these are figments of our imagination in a sense. It's what we see on the screen, but when this is compiled and downloaded into the controller, it goes down as machine level language. and there may be some earmarks on it as a process of reversing and uploading. RSLogix 5000 interprets it as ladder logic diagram, function block diagram, sequential function chart, or structured text. I really don't know all the details in what Rockwell Software is doing in that regard. But we're headed to bit instructions, and specifically the one-shot. So we'll drop this down a little bit. There's no reason to drop it down. We'll leave it up here. The one-shot ONS enables or disables the remainder of the rung depending on the status of the storage bit. That's really a good way to describe it. The one-shot instruction is one of my favorites. As a matter of fact, to me, for all of the simple instructions like truth on, truth off, energize output, latch, memory location, unlatch memory location, at those levels, the one-shot to me is fascinating because it's both an input and an output instruction. It reads a memory location and it writes to a memory location. If it reads the memory location and the memory location is off, then it writes to that memory location and turns it on. You need to think of all of these instructions, even the simplest ones, as a type of subroutine. These instructions have backing them a chunk of code. It's not just a mnemonic that goes to the controller that says ONS. What gets compiled and downloaded is a little routine that does exactly what this instruction does. Same thing with truth off, truth on, energize output. For instance, the OTE has a true and a false execution. If the rung is true, the code that backs that OTE instruction says if rung out is true, then set this memory location to 1. Else, if rung out condition is false, then set it to 0 or reset it. It's actually a little chunk of code, but you don't see that code. And of course, the code for a truth on, truth off, energize output, or even a one-shot is a very small amount of code. But there are other instructions. I don't want to get too far off the beaten path here, but if I go to, we'll just look at the tag. We won't look at the actual instruction of a predefined. We'll take the very first one and double click on it. We're going to have to bring this out of the way. You see that the data structure for an alarm instruction is 96 bytes. And the alarm instruction has code in it that manipulates, it reads certain values and sets certain values in this data structure. So it is a massive chunk of code that's really like a little subroutine, but you don't see it as a subroutine, you simply see it as an instruction. There's also enhanced alarm instruction. We'll stop right there. Simple enough. I think you get the idea. So we want to go back to our help screen. Well, I guess it disappeared. No, I moved it off. I didn't realize it would move completely off. I have two screens. And when I moved it over here, I guess it liked the other screen better and it just jumped over there. So back to the help screen. We'll put this other stuff back in there later. Here we've gone to the one-shot, the ONS. And to get right down to the meat of the matter, you want to get down to the bottom here where it shows execution. Pre-scan, the storage bit is set to prevent an invalid trigger during the first scan. That's interesting. Never noticed that before. Learn something every day. I love to learn something new. I know how that works and I use it very effectively. But this makes sense. A pre-scan means that when you put the processor in the run mode, it does a pre-scan. And we've looked at instructions before and we had them illustrated in the manual that showed pre-scan, run condition in is false, run condition in is true, and post-scan. We've seen this before. In this case, the storage bit, which would be this bit right here, a one-shot instruction has to have a tag to work with, a Boolean tag. It can be a single bit of a double integer, single integer, integer, or it can just be a Boolean. But you have to have a bit, and that's the storage bit. That is the bit that this instruction reads from and writes to. So that storage bit on the pre-scan is set, meaning set to 1, to prevent an invalid trigger during the first scan. What that means is, and the way the one-shot instruction works is, when the rung goes true, the one-shot reads that storage bit. If the bit is on, then the one-shot doesn't do anything. It has a false out, so that add instruction will not execute. So when this goes true, if this is set to 1 already, then this is false out. That's why the storage bit is set to prevent an invalid trigger during the first scan. The rung condition out is set to false. Okay. Now, rung condition in is false, the storage bit is cleared. This is under normal circumstances. If this is false, whatever's coming out of everything in front, everything to the left of that one shot, if this is false, then that's cleared. It's set to 0. The rung condition out is set to false, so it does not execute this part of the rung. Post-scan, the storage bit is cleared, the rung condition out is set to false. Now the rung condition in is true is a little bit more complicated. We can go to the flow chart and discuss this, but instead I'm just going to say when the rung goes true, if this is cleared, in other words not set, then it sets it and the rung out condition is true and it continues. If rung condition in is true and this is already on, in other words it's already been set, then the rung condition out is false. That's why it's called a one shot. So that's enough of help for that instruction. Now there's 2 other instructions that we're not going to spend a lot of time on, but you can see it's much more involved and the execution is a little bit different, and even the instruction is a little bit different. So you're actually using one-shot rising. You have a storage bit and an output bit. You use the output bit as a bit that goes on when this went from off to on. One-shot rising. One-shot falling would be just the opposite. We're going to leave it there. We didn't go that far in the manual. Moving on, I've gleaned the important points from the help file for you in the manual. In the future, you should be able to find your own way back to the instruction help files on your own. The one-shot instruction, the ONS, enables or disables the remainder of the rung, depending on the status of the storage bit. When enabled and the storage bit is cleared, the one-shot instruction enables the remainder of the rung, or has a true out condition for the rest of the rung. If something else is false to the right of the one shot, well, the rung's all done anyway. When disabled, or when the storage bit is set, the one shot instruction disables the remainder of the rung, or rather to say it sets it to a false out state. So in the manual, I spent some time elaborating on the flow diagrams for the one shot in detail. I break it up into a trigger, a hammer, and a bullet. Okay, or a round if you like, ammunition. In the Marine Corps we called them rounds, we didn't call them bullets. Bullets, basically the thing that you stick in the end of the cartridge, and hopefully you got some powder in there and you have some primer or something to detonate it. But I call it a bullet just because that's probably more common. So when I think of a one shot, I think of a one shot pistol or a one shot rifle. Once you cock it, you pull the trigger, it fires once and it won't fire again until you reset everything. Now this is the most powerful of the bit instructions, and it has become my favorite. If you use it correctly, it will do absolutely amazing things for your code. However, if you use it incorrectly, it will give you hours of headaches. You may set something in motion that you won't find out about for months or even years. It may cause intermittent problems in your code, and the problem disappears. It has an instance of that problem, but by the time you come out to troubleshoot it, there's no hint of it left. You have no idea what caused this machine to misbehave. You don't know if it was the machine mechanically has a little hitch in it somewhere, or if your code has a little nuance that you didn't see. When you use one-shot instructions, you need to follow the rules for the one-shot instruction. They can be found in the help files. I had you create a rung in your main routine. So we're going to close up the predefined. We're going to open up the main routine and create that rung. Back we are with the rung. However, let's geyser this up so it's easier for you to see on your mobile device if that's what you're looking at. I created a rung that has a true if on, a one-shot instruction, and an OTE called bullet. So I have a trigger, a hammer, and a bullet. And on a gun that you cock the hammer. And so we'll call this a single action one-shot, well, what's called a one-shot gun. We have a trigger, a hammer, and a bullet. If the hammer is cocked and you pull the trigger, it fires. If the hammer is not cocked and you pull the trigger, nothing happens. When the trigger is released, run condition in false, a fresh round is placed in the chamber. The storage bit hammer is set to 0, unfired, and the bullet is set to 0. When this goes false, the very first program scan where this is false, this instruction, with a false out of this instruction clears that bit. It clears the storage bit. This out is false, and the false execution of an OTE is to tell the memory location that it is pointed to by bullet, you're off, you're 0. When the trigger is squeezed again, run condition in true, the bullet is fired, set to 1, with a single bullet. If the trigger is not released, in other words, if you're still holding down the trigger, then nothing's going to happen. The run condition out is set to false. In controller time, remember this is a 20 microsecond scan time. So you set this true, this instruction, this is off, it sets it to 1, out is true, and it turns that bit on. But 20 microseconds later, if you have not released that trigger, meaning gone back to false, if it's still true on the next scan, then it looks here and it says, oh, hammer's already set to 1. You've already been fired, and then false out, nothing happens. Well, false out, it sets that to 0. So let's do that again from the beginning. When this goes true, the very first scan that this is true, the one shot looks at the storage bit. If it's on, then it's false out. If it's off, it sets it to 1 and sets true out. The true execution turns this bit on. The next program scan, if you're still holding down the trigger, in other words, it's still on in the very next scan, then the true out comes here. This instruction reads the storage bit. If it's on, then it sets false. If it's off, then it says true. Well, nothing ever cleared this because this never went false. So the false out here is going to cause the false execution of the OT, and it's going to be set to 0. And it's going to stay that way as long as this is true. Eventually, you're going to let off on the trigger. In the very first scan that this is off, then this will be false. False out clears this bit, and it has false out, and of course this is already off, so it doesn't really change anything, but it still does the false execution. When this goes true again, the very first scan that it goes true again, is true out. This reads the bit. Because the bit is off, it sets it to 1 and sets the out condition to true, turns this bit on. That's the true execution. Next program scan, this is still on. The one shot reads the bit, it's still set to 1. False out, the false execution is to turn that bit right back off. That bit, bullet, is going to be on for one program scan and one program scan only. Okay, save your project, beginner, L, processor number, one shot. So I'm going to save it, file, save as. I probably should say save as, so you don't actually hit save and then you save it as L35E or whatever you had in there before. So underscore one shot, and because we might change this program some more, I'm going to do a 0, 0 after that, just in case I have one shot 0, one shot 1, one shot 2, etc. Save. Go to view in the main memory and select watch. We need to go online. We need to download this and go online. So I'm going to go to communications, who active, processors picked, hit download. Did you notice how much faster that was? What did we change, or what did I change, that would make the download process much, much faster? Hint, L35E. I'm now plugged into the Ethernet port at 100 meg versus 38.4K baud rate. Now, if you're using an L31, not to worry, your download's still going to take longer. If you want to upgrade your L31, and we have some in stock and you want to purchase one, personally, I would probably look for one on eBay and get one from a reputable vendor out there that sells used PLC, or you can hedge your bets and go to your local Allen Bradley distributor and buy a brand new one. If you have the funds to do everything with brand new hardware and buy it all from the local Allen Bradley distributor, I would, because then you have their support. Okay, if you buy it used on eBay and you call up the technical support person at Rockwell or Allen Bradley or your local distributor, you may or may not get good support. Normally, most Rockwell Automation distributors are really good at bending over backwards to help people with Allen Bradley hardware that didn't buy it from them, simply to gain you as a future customer. At least the distributor that I worked for in Michigan, Kendall Electric, they bent way over backwards to help anybody with any problem. I've even seen their technical specialist help people with products that weren't Allen Bradley products, just because they were standing there, the customer had the problem, they knew how to help, and they helped them. Keep that in mind when you're buying hardware, PLC hardware, PAC hardware, that if you buy it brand new from the distributor, you're more likely to get support than if you buy it on eBay. I buy most all the used stuff on eBay naturally. A Rockwell Automation or their distributors do not sell used hardware. Here we are back with it downloaded, and we're in the run mode. Are any bits, oh, I forgot to turn on the watch. View, watch. Okay, there's our 3 bits down there. Now I'm going to drag this up so it's closer to the rung. I think I had you do this so if you want to do a screen capture or something, but the bits here are obvious. There's your 3 bits of memory. Here's your 3 bits of memory, bullet, hammer, trigger. Now they're not in the order that they are here. It's trigger, hammer, bullet. They're in alphabetical order, but it really doesn't matter. We can see them here, we can see them here. Are any of the bits on in memory? No. If so, which are on? None of them are on. We have not aliased any of these tags to members of a module-defined data type, simply to emphasize that they are just bits in memory. Whether they were module-defined tags or just internal tags, they're just bits in memory. Some bits, like module-defined tags, they are influenced, some of them, by input field devices, and some of those bits in memory that are module-defined tags influence output field devices. From your keyboard, toggle trigger to the on state. Now, you could throw in that code that I showed you in the last section, the just for fun or the challenge 1. You toggle it and it only goes on for a short period of time. We'll toggle it on and leave it on. Okay? But let's answer some questions. Are any of the bits on in memory? Yes. If so, which ones are on? Trigger and hammer. We can see both of those are on right here. That's true if on, so it's on. If this is highlighted, then it's on, and you can see it here. They're both set to 1. Why are they on? Well, this is on because I toggled it on, and I did not toggle it back off. This bit is on because I toggled this on, the true out state from this instruction, rung true out, or true rung out, however you want to say it, set this bit to 1 because it was not already 1. In other words, this instruction read it, it was off, so it set it to 1 and then set the rung condition out to true. Now, this is not on, but it was on. Remember, this is only on for one program scan, 20 microseconds. There's no way in the world that you could possibly see that go on for that period of time. I don't even think accidentally, if you hit it just right, that the screen would update. It's possible that if you just kept doing this, you might see a flicker there once in a while. But remember, I explained that it has to do with the refresh rate of the monitor, the electronics in the computer, everything. Did the bit address the memory as bullet change state? Well, the answer is yes, but you have to take that on faith. You have no way to prove it. You had no way to observe it. In order to know for sure whether or not the bit bullet change state, we need to create a 1-scan bit capture. This will be an online edit. Now, there's several ways you can do this. I use the counter instruction to do it, but you could have used the add instruction because if it's a one shot, it's only going to increment once. But we won't do that. We'll do it the way I did it. So I'm going to put this in the edit mode. I'll go to bullet. I'm going to go up here to timer counter. Now, there's only one kind of counter. There's not a count up and a count down. Those are instructions. There's counter data types, just like there's one timer data type that all three of these instructions work with. One timer data type, one counter data type. But we want to count up. We'll pick a count up, and I had you call it one-shot count. And again, it's good to learn to use upper lowercase delimiters. You can easily read that one-shot count, but you're not eating up memory space and making wider, longer tags by putting underscores in there. And you can never use spaces. If I put a space between one and shot, and count, it will look like 3 separate tags. We want to right click on this, new. See, it knows it's a counter. It's a counter instruction that assumes you want a counter data type. It's in the main program, so hit create. And we don't want a preset because we don't care whether it's done or not. Finalize all edits and set the preset to 1000. Well, I told you one thing and did another. So we'll set it to 1000. It's still going to work. It'll still count up whether it's done or not. But since I told you that set it to 1000 keeps the done bit set to 0, remember that the counter cannot increment unless the rung is true, and the rung's true state sets bullet to 1. So we're going to finalize all edits here. And we do have to agree on something. We can open up one-shot count here so we can see the accumulate right there. So there's bullet, hammer, here's the one-shot accumulate, and down here's trigger. Now I'm going to clear this. In other words, I'm going to toggle this off. So watch what happens to hammer and trigger. Okay, now they're all 0. It did not affect the accumulate. So we do have to agree on something because you're not going to be able to see it. And that is for this instruction to have responded to a true out condition from this instruction and write a 1 to bullet, then this had to be true, and hence out of here had to be true. So if this shows an accumulate of 1, then we know this had to be true. This rung had to be true and bullet had to be on for 1 scan. From your keyboard, toggle trigger to the off state. We already did that. Are any of the bits on in memory? No, they're not. From your keyboard, toggle trigger to the on state. Are any of the bits on in memory? Yes. There are 2 bits on in memory. Now we're not counting the accumulate as a bit, but the hammer is on and the trigger is on, right? You can see that down here and you can see it up here. Did the bit addressed in memory as bullet change state? Well, you didn't see it change state. You have nothing right now to prove it ever changed state. But because the counter shows an accumulate of 1, you know it changed state. So this is like a bit trap, if you like. If you're ever working with one-shots, this is a very simple one-shot that has one precondition, no post-conditions. Because remember, just because this instruction had a true out doesn't mean that other instructions in between here were also true, because if they were false, then this was false, it turned it off, and nothing ever happened with bullet. But we'll get into that later. Preconditions, postconditions. If you were not sure about the last question, open up your program tags database and expand one-shot count. From your keyboard, toggle trigger to the off state. We already had this expanded. Are any of the bits on in memory? No, we're not counting the accumulate, but hammer is off, trigger is off, and bullet is off. They're all off. Did the bit addressed in memory as bullet change state? No, it did not. What is the accumulated count in one shot? Accumulate value. 1. From your keyboard, toggle trigger to the on state. Are any of the bits on in memory? Yes. Hammer is on, trigger is on. Did the bit addressed in memory as bullet change state? You're going to answer yes, because the accumulator is now 2. What is accumulated count in the one-shot count? 2. How do you know that the bit addresses bullet change state? Now, I keep telling you why, but you need to say it to yourself. You need to think it to yourself. So remember, when you're in the field and you're troubleshooting a rung that has a one-shot instruction, you can't go and look at it and know that it went on. You really can't. You can't know that this went off and back on while you were doing something else. If you left it and it looked like this, ignore the count up. It's not really in there, not out in the field. You don't know whether this has trigger or not, because that bit's not on. That's why you need to add a count up or an add instruction that increments by 1. In other words, you create a tag called one-shot count. What the heck, we'll just do that. As long as we're here, we'll probably end up doing it again later in another. Drag this out a little bit. Compute. Add. Well, now we're too big, so we'll geezer down a little bit. And we'll drag this bad boy over this way. Geezer down one more time. Now, I'm going to create a new tag, and I'm going to call it one-shot count, but it's a different tag name, so we know that they're not interacting. Double integer. I'm going to put in a 1 for the source B, and then I'm going to put one-shot count down below. So whenever this run goes true, one-shot count will add 1 and store it in one-shot count. So if one-shot count is 0 and adds 1, then it's 1. If one-shot count is 1, you add 1, then it's 2. What's different about these two instructions is, although they're going to look like they're behaving the same, this one has a built-in one-shot. In other words, if this were used in a rung with conditions, when the condition goes true on a false to true transition, this will increment by 1. It'll increment that counter data type. This instruction will do it every single time the rung's true, whether it's going from false to true or what. If the rung's true, so it becomes a scan counter. It's going to count up 1 on every single scan. Without a one-shot in here, you don't want to use an add like this. We're kind of deviating a little bit from what's interesting. I don't see that in there. So let's go up to view and hit watch again. Okay, now we've got it in there. Okay, and there, that should be our count. So now we can watch all of these. But I'm going to finalize all edits. Change it back to the watch tab down here at the bottom. And we can see all the instructions, and we can see it down here. Okay, now I'm going to set this back to 0. These both have the same count. Then I'm going to toggle the bit off. See, nothing happens over here. Toggle the bit on. See, they both read 1. Toggle the bit off, toggle it back on again. Okay, see, now they're both 2. So that's 2 ways that you can trap the true occurrence of a one-shot. In other words, if you set these to 0, you go run the machine and come back, and this is set to 1 or greater, then you know that this thing is cranking away. It's firing bullets, even though you can't see it when you go look at it. Did the bit addressed in memory's bullet change state? Yes, it did. What is the cumulative count? 2. How do you know that the bit addressed as bullet change state? Well, we showed it in 2 different ways.